Okay, it's our pleasure to have Dr. Kannan visiting us all the way from MIT. And Dr. Kannan obtained his master's degree in physics in 2010 from the Indian Institute of Technology. He went to Max Planck Institute for Astronomy for his PhD study under the supervision of Dr. Andrew Margio and Dr. Greg Stevenson. Red, who joined MIT in 2014 as a postdoc fellow, working with Professor Mark Webbersberger. Red's research focuses on the theoretical and numerical modeling of galaxy formation in a cosmological context. Today, he's going to talk to us about how X-rays from the hot intercluster medium affect the radiative cooling rates of gas in galaxies.
Thank you. Thank you so much. So as mentioned, I'm a postdoc at MIT, and I'll be talking about X-ray radiation quenching, which is basically looking at what the X-ray radiation from clusters, the cluster ICM, how it affects the hot halo gas surrounding the satellite galaxies in these clusters. So as an introduction, let's look at what actually exists out there, so how people have tried to model satellite quenching in the literature. So we all know that galaxy environment plays a major role on the properties of the galaxies itself. So there is a marked difference between the properties of field and satellite galaxies, especially in their star formation rates. So at low masses, so you can see the plot here, there's a stellar mass versus quiescent fraction. The points are the observational points, and the lines are semi-analytical model trying to reproduce the observational points. And if you look at the satellite quiescent fraction in observations, which is this green line here, and what their model predicts, it's very, very different. But the observations do show that satellites generally are more quiescent, but not as quiescent as the semi-analytical model predicts. This is because these models have a very crude and an approximate way of describing this phenomenon, and it seems that their quenching rate or gas stripping rate is quite high, and that is why you get this discrepancy in semi-analytic models. If you go to hydrodynamic simulations, here I show the result from the illustrious simulations, which was published by Mark. So here, as a function of stellar mass and which is called the overdensity parameter, which basically is a parameter which defines the environment of a galaxy. If this parameter is high, then it's in a much more denser environment. Okay, so the contours are from the simulation, and this solid white line is from the observational Peng et al. Paper. Here, what happens is that the observations say that within this contour, 90% of the galaxies are quiescent above this contour, whereas only 40% of the galaxies are quiescent in the simulations. So gas stripping, which is one of the main factors which is attributed to satellite quenching, should be theoretically well modeled in a hydrodynamic simulation. There is no reason why it should not be modeled correctly, right? If you're doing hydrodynamics right, then you should get the gas stripping right as well. But what happens, which is so here they overproduce the quiescent fractions, whereas in the observations we underproduce the quiescent fraction. So what is the mechanism which quenches these satellite galaxies? So one of the few papers which has observational papers which has tried to address this is this Peng et al. 2015 paper, where they look at the metallicities of stars in the passive versus star-forming galaxies. And they find that almost in all cases, the passive galaxies have much higher metallicity than the star-forming galaxies. The stars in passive galaxies have much higher metallicities. And they argue in this paper that this difference can only be explained if satellite quenching takes place through strangulation and not through fast quenching processes. I'll explain what strangulation means. So this is a plot from their paper. So if you have quenching due to gas stripping, that is the first timeline here. So if you are quenching due to gas stripping, then you have a star-forming galaxy, and then you strip the galaxy of most of its gas, and then it becomes passive instantaneously. Whereas if you have quenching by strangulation, you have star-forming gas in the center, but then you do not allow any more gas to cool to the center. And the rest of the gas, star-forming gas, forms stars, and then it becomes quiescent without adding any more additional gas. So what happens is that the star formation is recycled through the so the metallicity in this case increases because there is no amount of additional gas coming through. So this is the only avenue through which you can explain this kind of difference between passive and star-forming galaxies, the metallicity difference between passive and star-forming galaxies. Of course. So one way you can remove, this scenario can be possible is through stripping of the hot gas reservoir. Rather than stripping the gas from the center of the galaxy, you just strip the reservoir. But then this process is found to be really, really slow. For example, in the numerical simulations from McCarthy et al. Have found that even after 10 gigayears of a satellite orbiting for typical satellite and main galaxy parameters, you still have 30% of the hot hello gas remaining even after 10 gigayears. So this process is really slow. Another way you can stop gas from getting to the centers is if you stop gas from cooling. So if strangulation can also occur if the gas reservoir is prevented from cooling to the centers. Okay. And one of the ways you can do this is through radiation fields. So radiation fields can suppress gas cooling. Generally, in almost all of the simulations that you have seen so far, the gas cooling is calculated in the presence of a spatially constant ultraviolet background only. Whereas local sources can have a huge effect. And this is shown by various authors, especially from stars and from AGN as well. So let's look at how radiation fields can suppress gas cooling and gas cooling in general. So on the left-hand side, I show the cooling curve, the total cooling curve, which is the solid black line here, and the colored lines are the individual contribution from each individual element in the gas. So under collision and ionization equilibrium, the solid black, this is the total cooling curve of the gas for a solar metallicity gas. Okay. Whereas if you have just the UV background, then it gets rid of the hydrogen peak and a little bit of silicon and carbon, but the oxygen, ion, and the neon peaks remain. And in order to get rid of this cooling as well, you need energies of this order. So you know the O4 plus 113.9 electron volts in this regime. You need radiation fields in this regime in order to negate the cooling from these ions, right? And this is basically in the soft X-ray regime. So you basically need soft X-rays in order to reduce cooling from metals and not only from hydrogen and helium. Okay. So what are the X-ray sources? The X-ray sources that we will consider. First, let's look at the cluster X-ray radiation field from clusters. So the clusters are basically extended sources of radiation. They have really high luminosities, tempo of 43 to 46 hertz per second. And this is just a paper by Anderson et al. As a function of the stellar mass of the central galaxy, he plots the LX. And as you can see, it has very high luminosities. So how do we model the X-ray radiation fields in our simulations? So we try to do the most simple, in the most simplest way possible. We just look at the BREMSSTRAHLUNG radiation and not any emission lines. So which is given by this formula. So and we can just see by inputting the density, metallicity, and the temperature of the gas from the numerical simulations can we recover the observed effect. So you can indeed do that. So what you can do is you can construct clusters of mass 10 power 14 and 10 power 15 solar masses, you have the dark matter in a Navarro-Franken-White profile, gas in hydrostatic equilibrium with the temperature set to the virial temperature of the halo. And then you calculate the BREMSSTRAHLUNG emissivity using this formula, and then the blue points of the observations and the red square and the red triangle is the luminosity calculated from our synthetic clusters. Okay, so you can kind of reproduce the X-ray luminosity just by doing very simple setup. Okay, so if you have this kind of luminosities, X-ray luminosities, what does it look like? So you can all in the same way you can also calculate the flux, which is photons per second per centimeter square, as a function of energy, as a function of radial distance from the center of these clusters. So for example, for the massive cluster, which is 10 power 15 solar masses, I calculated a distance of 1 megaparsec, 300 kiloparsecs, and 100 kiloparsec, what the radiation flux is as a function of frequency. And to see how much it is different, you see this is the UV background that most of the people use in the simulations. So you have a lot more flux than is what is actually used in these simulations to calculate gas cooling rates. And none of the simulations take care of this flux while doing these numerical simulations. So, and then if you put this flux into cloudy and then ask how does the cooling rate of the gas change, this is the result. So I showed the cooling function as a function of temperature, the cooling rate. So if you have, if the gas sees only the UV background, then the purple line here is the cooling rate. If it sees X-ray radiation flux at 100 kiloparsecs, then you almost get rid of almost all metal line cooling, and you're only left with BREMSSTRAHLUNG cooling, and that's this line here, right? So the thing to note, however, is that it only reduces cooling in gas below 10 power 6.5 Kelvin. Above that, it's all BREMSSTRAHLUNG cooling anyway, so you cannot really you cannot really reduce the gas cooling. You can maybe boost it a little bit due to inverse Compton scattering, but below this is mainly where the radiation field affects the gas cooling rates. So how do you implement this gas cooling dependent upon the radiation field in simulations? So the implementation is quite difficult. So if you want radiative transfer coupled with hydrodynamics, then most of the algorithms are really very inefficient. Many people do it using the gray FLD approximation, which basically means the opacity is constant, irrespective of the frequency, which is certainly not true in our cases. There are some multi-frequency radiative transfer codes, but they usually do it in post-processing. And even if they do it coupled with hydrodynamics, they usually tend to stick to reionization. They cannot go much farther because it's too computationally intensive. And multi-frequency is extremely important because you're looking at frequencies all the way, which are frequencies which can affect cooling all the way from 10 power 4 to 10 power 6 Kelvin. So you need multi-frequency radiative transfer in order to do this. And if you do RHD, then you also need to calculate the gas cooling rates on the fly, which amounts to solving about 130 coupled ODs per particle per time step. So what I'm getting at is it's really computationally expensive to do it accurately. So what we do is a very simple approximations. So what we do is we take advantage of the fact that most of the gas is optically thin to X-ray photons. Of course, you cannot expect the ISM of the galaxy to be optically thin. So if any of our sources are in the gas disk itself, then we assume that there's an escape fraction for low energy photons. We assume that only 5% of the low energy photons escape. So whereas the rest of the gas is optically thin. So this reduces our problem to an inverse distance square problem. And this also allows us to tabulate the cooling rates instead of calculating the cooling rates on the fly. So this was implemented, and you can look at these papers to see how exactly this was done. So first, let us look at the results of coupling radiation fields to the gas cooling rates. So this is from a previous paper where I look at I simulate a Milky Way type galaxy, and then I look at the star formation rate with and without the local radiation fields turned on. Here, local radiation field is just due to star formation, X-rays from supernova heated bubbles, and post AGB stars. And you can see that if you include these local radiation fields, you can reduce the star formation by quite a bit, and you also increase the stellar mass by about 30 to 40% in Milky Way mass galaxies. Now let's look at what the cluster radiation field can do. So here I plot. So it's a single test particle. It's not coupled to any hydrodynamics. I just evolve it with time, and I allow the particle to cool, either in the presence of a UV background or in the presence of UV background plus some cluster radiation field. So the UV background plus cluster radiation field is given in the green lines, and just the UV background is the blue line. Okay, so and for different density of the particle. So if you look at a low density, if the particle starts at a really high temperature, then the cooling time between the particle experiencing only the UV and the UV plus the cluster radiation field is really small. The maximum effect you see between 10 power 6.5 and less than 10 power 6.5 Kelvin is the gas which is affected most by these cluster radiation fields. What this also means is that the cluster radiation fields are optically thin to their own radiation field, but they can essentially impact any satellite galaxies where the virial temperature is less than 10 power 6.5 Kelvin. So what it means is that although it does not affect the dynamics of the cluster cooling flows, it can affect the dynamics of the cooling flows in the satellites within the clusters. So I ran a simulation of a galaxy of mass 10 power 11, 5 times 10 power 11, without ramp pressure stripping or tidal stripping. So it just experiences a radiation field. I put it at a distance of 100 or 300 kiloparsecs from the center of the cluster, and I look at how much amount of cold gas is formed in this percentage change in the amount of cold gas formed between the runs where only the UV background is turned on and the UV background plus the cluster radiation field is turned on. As you can see, if you place it at a massive cluster, which is the solid line, if it is a smaller cluster, then the radiation field is not as effective. That's the dashed line here. But if you place it at a massive cluster, 10 power 15 solar masses, then as you go to lower and lower, as you go closer and closer to the cluster center, you can reduce the cold gas fraction by a huge amount, by 40 to 50%. And it's only about 10 to 20% in 10 power 14 solar mass halo. And let's see how this simulation does with ramp pressure stripping. So now what you do is you have a cluster and you let the satellite galaxy fall into the cluster, and everything is turned on. So you have ramp pressure stripping and all those effects in addition to your radiation fields. Here also, you see the solid lines are the total stellar mass, the dashed lines are the star formation rate as a function of time, and the red is the evolution with the cluster radiation fields included, and green without the cluster radiation fields. And this is all done self-consistently within the simulation. So you can see, even in the presence of all these other environmental effects trying to quench the galaxies, the radiation fields do reduce the stellar mass by about 20% within a giga-year, that is, and it reduces this, and the star formation is consistently lower by about 20 to 30% just due to these cluster radiation fields. These were just very ideal setups. Now I have also looked at real cosmological simulations, and I look at a 2 times 10 power 15 cluster at redshift 0. I look at and it has all the physics which is in the illustrious simulation, and I look at the stellar mass halo mass function. And you can see the satellites in general are a bit lower stellar mass than in the UV plus the cluster radiation field run rather than just the UV. You can see this a bit more nicely where I plot the fraction of the stellar mass in satellites formed in the UV plus the cluster run divided by just the UV run, and you can see the stellar mass in all the satellites formed is about 20% lower. And also you can also see this by matching the halos in the two runs. So it's essentially the same run with and without the cluster radiation fields. So you can match the satellites from one halo to the other halo. And so I have matched the satellites here. So in almost all cases, except this one satellite here, in almost all the satellites, you turn on the radiation field and you get a reduction for about 20 to 30% in the stellar mass of the halo. So this seems to be a really good mechanism to quench satellite galaxies. There are still things to do to see if you actually get higher metallicities, which is to see if you can match observations and see if passive galaxies are much metal enriched. And also if you need to perform a really large scale volume simulation with hundreds of galaxies in order to see if you get the correct passive fraction as a function of the cluster distance. So in conclusion, I would like to say the cooling radiation is from the ICM can significantly modify the cooling rates of low temperature gas, relatively low temperature gas. So this largely suppresses cooling in lower mass systems, especially satellite systems within the cluster galaxies. It reduces the star formation in satellites even before they are stripped of gas through ram pressure stripping or some other process. And it's a very promising candidate for satellite strangulation. Thank you.
So your suggestion is that the inclusion of this X-ray energy will reduce the cooling rate? Is that
yes.
what you're saying? I don't understand that, because normally the cooling rate is the number of atoms that are in the upper state times the Einstein A coefficient, and you have two sources of excitation, collisional and then the ionization or the excitation from your X-rays.
Yeah.
And so why would that wouldn't that make the cooling rate higher in terms of lambda ergs per centimeter cubed?
No. So that's exactly the cooling rate, right? Here, you have collisional excitation. All processes are considered here. Okay. So if you don't have the X-ray radiation fields, then it's the purple line. You have these. So you collisionally excite, whereas you collisionally de-excite as well. But if you have X-rays, then you basically have BREMSSTRAHLUNG, because you no longer have atoms with electrons in them. It's just plasma moving around. So as you get rid of atoms from the electrons from the atom, you reduce the channels through which it can cool, and so your cooling rate reduces.
So you're going to drive these, ionize these beyond this fine structure line excitation. Okay.
You noted early on that you got a good fit just using the BREMSSTRAHLUNG,
Yeah.
which is certainly going to be true once you get above about 2 keV.
Okay.
But an implication of this is you can make a plot of what the line to continuum ratio is as a function of temperature. And as you go down to lower temperatures and less massive clusters, that completely changes and it becomes line dominated in the BREMSSTRAHLUNG, which would predict that you get almost a phase change in the results, because the differences between the BREMS and the line. It also suggests, by the way, another way of approaching the same problem, because really what you're doing, if you go back a couple of slides, is just knocking out a couple of your key cooling ions.
Yeah.
I mean, all that you don't really care about the background per se, as far as I can tell. What you care about is whether or not those ions exist or not. And so you can look at that just in terms of what the radiation transfer is of just the photons.
Just the photons from those ions.
Right.
Yeah, so I have just mentioned 3 ions here, but in order to get this whole 10 power 4 to 10 power 6 correct, you need 11 different ions, 11 different elements, and all their ionic species.
Not all their ionic. Trust me, I know.
Okay. So this paper, especially this one, argued that you need these 11 different elements and the species in order to get this whole thing right. This is where this 130 ODEs comes from. It's exactly from that paper.
Right.
But they argue that you need this to get this cooling curve right. But if not, then yes, I'm open to suggestions.
Well, the graph there shows that 90% of the cooling is coming from oxygen 6 at 10 to the 5, for example.
Yeah, that's true.
So that one ion.
It's not just oxygen 6, it's all of oxygen.
No, it's mostly oxygen 6.
Okay. Okay, yeah, maybe you can just look at the individual ions and maybe be ready to transfer just for those.
Any other questions for Rahul? If not, let's thank Rahul.
Okay, our next speaker is going to be Boris Gaensicke, who's joining us from the University of Warwick in the UK. Boris is going to be visiting us for all of today, all of tomorrow, and all of Friday. I'd like to have the opportunity to meet with him. Do sign up, and I'll resend around the sign up sheet again for people. So Boris is going to be speaking at tomorrow's ITC luncheon, and also giving the main CFA colloquium tomorrow. And the main CFA colloquium is going to be on planetary systems around white dwarfs and pollution of white dwarfs. But today, Boris is going to be talking to us about the progenitors of 1A supernova.
Okay, thanks for having me here, and this is a slightly maybe provocative initiative to talk about type 1a supernovae. Okay, so why do we really care about supernovae? Well, you have all seen this, that the universe is made up of a lot of nothing. And it has been discovered, or at least supernovae have contributed largely to that, and that's type 1As. And there are two main channels. They're either double degenerates or single degenerates, and maybe I could just call for a quick show of hands. Who of you believes in double degenerates? And who believes in single degenerates? And who doesn't care? Okay.
How about both?
Or both, yes. So I'll talk only about, this is confusing because I've got a remote control that looks exactly like this, but obviously this is not my control. So the outline of the talk is this. I will talk a little bit about mass growth among single degenerates, about cataclysmic variables, which are low mass companions to white dwarfs, accreting onto white dwarfs, about failed type 1As, and a search for massive white dwarfs in pre-CVs. So the canonical idea for the single degenerate path goes back a long way to the kind of 1980s, where, or even actually earlier, this is an interesting paper and much neglected paper by Mike Shar from 1978, which is called Non-Injecting Nova as EUV Source, and the title is exactly what it means. And that is, if you look at the white dwarf mass and the accretion rate, you get a parameter space where you have classical novae that eject mass. I come back to that on the next slide. Recurrent EUV sources, which today we would call recurrent novae. And then you've got a regime where you accrete hydrogen onto a white dwarf just at the rate that you burn it. And so you have steady, stable shell burning on the white dwarf. And in that case, most people agree that you can grow the white dwarf in mass because that's what you want to do to reach eventually the Chandrasekhar limit. And so if people nowadays talk about single degenerate type 1a progenitors, they mainly talk about systems that are here, which are observationally called super soft sources, super soft X-ray sources or something like that, because they are steady shell burning and have temperatures of a few 100,000 degrees. or these recurrent EUV sources, so systems that are very close to the steady state burning strip but not quite steady burning. So those would be called recurrent novae. And in all of that discussion, cataclysmic variables, which look pretty much like that, so they have a low mass companion, typically an M dwarf or a K dwarf and a Y dwarf and an accretion disk, they don't need to apply because canonical wisdom based on theory primarily is that you accrete hydrogen onto the white dwarf, it will settle, it will build up a degenerate layer, and eventually that degenerate layer ignites, and if you ignite nuclear burning in a degenerate layer, you kind of heat up without that the material expands until you lift degeneracy, and then you explosively blow off the accreted layer, and so you eject all of the mass that has been accreted, and these systems sit in this diagram kind of up here. Now these are the most common white dwarf binaries with the main sequence companion. So this is where the population peaks. Okay, so why do I say this is canonical wisdom? There are a lot of nova simulation, classical nova simulation. Most of them are 1D models. And they look at the accreted mass versus ejected mass. And so I took a kind of seminal paper by Pranic and Kovacs from 20 years ago, but things haven't evolved a huge amount since then. Models have become a little bit more detailed, but the basic conclusion remains the same. And that is if you accrete at rates of up to 10 to the minus 8, then with every single nova eruption, you lose mass. So what do I actually show here? So I show here the difference between accreted and ejected mass. So not only you eject all the mass that was accreted, but you dredge up some of the core mass of the white dwarf. And so in a single nova eruption, in this case, you lose of the order 10 to the minus 5 solar masses. And these systems undergo many hundreds or thousands of nova eruptions. And so therefore, the parameter space living over here should erode the white dwarf mass. And so you should go down in mass rather than go up. And therefore, cataclysmic variables aren't ever considered to be type 1a, viable type 1a progenitors. Now, this is theory. There are some people who have some nova theory, people who have published in the last year some kind of quite controversial papers where they say that some of these may need to be re-examined. So let's go to observations and to kind of some facts. And let's look at white dwarf masses in binaries, in single-degenerate binaries. Now, how does nature actually make cataclysmic variables or novae, or for that to say any type of type 1a progenitors? They all start out as two main sequence stars in a closed binary. They evolve, they go through a common envelope because the more massive star will fill its Roche volume and start mass transfer on the less massive star can't accommodate all the mass that it's given, and so you form a common envelope in which you very rapidly shrink the binary period and you end up with a compact binary down here. And if you want to make a double degenerate, well, then you do it a second time. You have that star evolving, becoming a red giant, and you go through a second common envelope, end up with two white dwarfs. Now, one very important thing that you see here is that you end up with a very low mass white dwarf in this example, 0.4 solar masses. Good. So what do we actually know about white dwarf masses? Let's look at single white dwarfs. This is a collection, is probably the highest, not the largest number, but highest quality selection of white dwarf masses of what are presumed to be single white dwarfs. It peaks very narrowly around 0.6 solar masses. And then you see there's a secondary peak at about 0.4. I come back to that in a minute. And there's a tail towards high mass, and you have very few high mass white dwarfs. And so some of them are oxygen neon cores from intermediate mass progenitors or results of merger. So these are single white dwarfs. The universe is actually too young to make helium core white dwarfs. And so the way that you make helium core white dwarfs is just as I showed you on the previous slide. You go through a common envelope, you truncate the evolution of the core, you don't ignite helium burning, you end up with a low mass helium core. And that really works. We've shown that a couple of years ago where we looked at white dwarf plus main sequence star binaries from Sloan. And we could show that systems that are in wide binaries that didn't undergo interaction, this is the black histogram here, have an average mass of close to 0.6. And systems that are in short period binaries, so that have undergone a common envelope, they have a lower average mass of about 0.5 or something like that. So the one-line summary is that common envelope evolution, which will lead eventually to type 1a progenitors, in the first place produces low mass white dwarfs. So it's hard to make high mass white dwarfs in that way because you make, okay. So next step. Now we want to look at the masses of white dwarfs in accreting, interacting binaries. So these are cataclysmic variables. They accrete from a low mass companion. And they have been subject to studies for the past 40 odd years. And there have been a number of studies that looked at the average white dwarf masses. And so you look at the numbers over 10 years here, they're all extremely high. So they're all above a solar mass. And that's way, way, way above the average mass of single white dwarfs. And these systems have been formed through common envelopes. So by and large, we would expect that this sample should contain some low mass helium core white dwarfs. And so the key question is, this is much larger than 0.6 solar masses, which single white dwarfs have on average, and what does it mean? Why are these stars so massive? Ritter and Burkhardt in 1986, they looked at all this evidence and they concluded that this is simply an observational bias. And the reason is the following, that the accretion luminosity per, basically how much energy do you release per kilogram of stuff that you drop onto a white dwarf, is proportional to the white dwarf mass over the white dwarf radius. Now white dwarfs are degenerate stars, so they are smaller if they're more massive, and they follow a mass-radius relation, like radius is proportional to m white dwarf to the power, some negative power. And so that means that if you go to higher mass white dwarfs, you get much more energy out of by dumping material onto them. And observationally, you should be biased to detect more massive white dwarfs. And that's where people stop. They say, well, we understand, that's fine. We understand that in a given sample, we should actually be more sensitive to more massive white dwarfs, and that's what we find, and that's good. Now, very few people have actually read the Ritter and Burkhardt paper carefully, because they went through a whole lot of simulations and discussion, and they said that that's true in a shallow survey. However, if you go to a deep survey, where your limiting magnitude is no longer a big problem, then the average mass should actually go down close to the average mass of single white dwarfs, because you get more sensitive to the much more common but fainter lower mass white dwarfs. And so they said, if you had a sample down to 20th magnitude, you should actually have no bias anymore. Now, 20th magnitude in 1986 was kind of visionary, because the magnitude limit there was about 15. But we all know what happened. Sloan came along and so on. And so here are a few measurements of white dwarf masses measured in eclipsing cataclysmic variables. So you see here eclipse light curves, high-speed photometry of cataclysmic variables identified from Sloan. And I don't go into the details, but you can measure from those accurately to about 5% the white dwarf mass. And they're shown here as a function of the orbital period of the system. And what you see is that they pretty much all of them are in the range of about 0.8, and some of them kind of up to 1.2. So even in a magnitude limited sample which goes down to 20th magnitude, the same effect is still there, that these white dwarfs and cataclysmic variables are just very massive. So how do things hang together? Now we have nowadays large samples of cataclysmic variables, and we can look at all the evidence for masses. And what I've done in this diagram is I show in black what I would call high quality measurements. So I would, well, at least bet a pizza that these measurements are correct to within 5–10%. And then there's a whole range of random measurements where I didn't even look how they were done. They're just taken from a big compilation where somebody stuck all mass measurements that were done in whatever ways into a table. The surprising thing is, the mean mass is actually the same. You only have a much larger spread. So these are just low quality measurements, but the mean remains the same. And then down here in that panel, I have post-common envelope binaries. So these are detached white dwarf plus M dwarf or K dwarf binaries. And they have, and I showed that a few slides ago, they have an average mass of about 0.5, because common envelope evolution typically truncates, stops the growth of the core mass. And so you end up with low mass white dwarfs. Now these systems here, not all of them, but some of them will evolve into cataclysmic variables, depending on mass ratio, age of the universe, and so on. So we did some cut and said which of these are actually representative of these guys up here, and so it ends up with this. And you see there's a clear trend that the actual cataclysmic variables are much more massive, the white dwarfs, 0.83 solar masses, then they're progenitors. If we say, and I come back to that later, that these are representative progenitors of these. So then the simple conclusion is something happens between here and here, because 0.6 and 0.8, you might say, well, that's only 0.2 solar masses, but that's a huge step. Why is it a huge step? Because there's a thing called the initial to final mass relation, and that's shown down here. Just ignore the crosses on there, they're irrelevant for now. So you have here the mass of the main sequence progenitor star, which goes up to about 8 or 10. If you go beyond that, you have a core collapse supernova and you form neutron stars. So these stars, they make white dwarfs, and you have here the final mass, the mass of the white dwarf. And so more massive stars lose a larger fraction of their mass, but they make still more massive white dwarfs. So white dwarf mass and progenitor mass are strongly correlated. And so if we look at a typical average mass of single white dwarfs, 0.6, we look at progenitors of about 2 solar masses. So we're talking about A stars, early F, late A stars. If we say, well, maybe all cataclysmic variables come from just main sequence progenitors, and they were born massive, and then actually eroded down by nova eruption. So they were born maybe with 1.2 and then eroded down to 1. Then we go over here and we say, oh, then we actually start to need kind of 5 to 6, 7, 8 solar mass. And these are kind of late to mid, early B-type stars. And then we would say cataclysmic variables have to have massive progenitors. But we know that these systems exist, which have gone through this phase, and they should become cataclysmic variables. So there's something funny there. So there are 2 ways out. Either, as I just said, we make cataclysmic variables having already massive white dwarfs at the beginning, and then we allow them to erode down by classical novae. Or white dwarfs and CVs can grow in mass. And then the question is how or when. And so both options have actually implications that you will bump up the number of potential type 1a progenitors you can produce in that path. So now I'll talk about failed type 1a progenitors. And to begin with that, I show 2 HST COS spectra of 2 cataclysmic variables. Now most systems that we observe look like that. You have a broad Lyman alpha line. You see the white dwarf here. So that's the white dwarf. You see absorption lines from metals accreting onto the white dwarf, and you have emission lines from the accretion flow from the disk. Highlighted in yellow are 2 important lines. Most stars that we observe, or most stars in general, are dominated by a carbon-4 emission line. A few of them, which I call anomalous here, they have no carbon, and instead they have a very strong nitrogen-5 line. So there's a complete reversal in the ratio of nitrogen to carbon fluxes. If we look at the UV spectra of genuine surface-burning super soft X-ray sources, and they're very few, then we see that these have strong nitrogen and no carbon. What's the reason for that? The reason is that the donor stars in super soft X-ray binaries are sufficiently massive that they have CNO burning, and you strip off mass from the surface until you at some point see the CNO processed material. And the CNO process, if you have inefficient CN burning, reduces carbon and enhances nitrogen. So through CNO burning in a star, let's say 1.5 solar mass and above, you reduce carbon, you enhance nitrogen, you rip off layers of the surface, you accrete material that is sufficiently deep down, and then you see these abundances. And so, by conclusion, we know that this system down here, which is now a cataclysmic variable with a star that looks like a 0.3 solar mass companion, that 0.3 solar mass companion was actually 1.5 solar masses or more in the past, and the system has gone through a super soft phase. So it should have been, I don't know if it was really a super soft X-ray source, but it should have gone through thermal timescale mass transfer at some point in the past. And so we can look at failed type 1a progenitors, which were on the right path, but then they ran out of steam and didn't reach the Chandrasekhar limit. And we can do some exciting stuff. So this is a bit work in progress. We can, and we do that with MESA, we can calculate the evolution of these systems, including mass transfer. And so time goes in this way. The system, this is orbital period. The system starts to be detached, goes into contact, evolves. You can see here the white dwarf mass grows because we go through a phase of steady burning. And then the mass ratio becomes sufficiently low that it stops thermal timescale mass transfer, it becomes a normal cataclysmic variables, and keeps on evolving like a normal cataclysmic variable. So you see here the companion mass, which kind of monotonously decreases, and the white dwarf mass, which increases by about 0.1. And that's what you would exactly expect. The second thing we can measure in the white dwarf photosphere, the abundances of the material from the donor star. And we can look at the carbon to nitrogen ratio. Like I show also the carbon 12 to carbon 13 ratio. We can't unfortunately measure that, but we can measure the C/N ratio, C/N ratio. And we see that for an evolved donor star where you strip off material, it will drop by 2 orders of magnitude or more, whereas that square over here shows how it would look if you accrete from a low mass companion that isn't evolved. So we can actually learn something about the actual evolution of systems that evolved towards type 1a but didn't quite make it. And then we want to do some statistics to work out like how many systems go actually through that path. And to do that, we need HST. And we had some programs in cycle 11 and 12 where we observed of the order 70 stars. And then STIS died. And that was really kind of unfortunate because we had time. And like 3 days after I submitted the phase 2, STIS packed up. And then there was a long gap, and we kind of restarted that in cycle 20 with a slightly different strategy, spending more time per star, because we will eventually, when we get Gaia parallaxes, be able to also measure accurate masses from this spectra, but that's kind of 2 years into the future. But for now, we can simply look at the fraction of cataclysmic variables that come through that channel, so that are failed type 1as. You see here in white a total period distribution of cataclysmic variables known. In green, the ones that we observed with HST, and in red, the ones that have an inverted nitrogen to carbon ratio. And order of 15% have gone through that path and so have evolved donors and go into that box failed type 1a. It doesn't mean that the others couldn't have done it, but maybe we haven't stripped far enough down to see the CNO material, but so 15% is kind of a lower limit. And then the last couple of minutes I want to spend on a search for, because basically I said, well, either you grow white dwarf mass already on the way to become a CV, and that would imply that all systems should go through that path. And here I say, well, lower limit 15%, to go from lower limit of 15 to 100% is hard. So maybe we make some CVs in the first case with high mass white dwarfs. And so we embarked on a search for progenitors of cataclysmic variables, detached white dwarf plus M dwarf main sequence binaries with massive white dwarfs. And it turns out that's actually hard work. It's easy to find white dwarf plus M or K star binaries. And so we've done that using the Sloan survey for kind of a number of years. And what you do is you plot a color-color diagram. This is U minus G, so that's a very blue color. This is G minus R. This is a color more towards the red. And you have here the main sequence. M dwarfs are down here, so these are all single M dwarfs. That triangle up here are single white dwarfs, and if you stick both of them together in an unresolved binary, you get a mixed color. And so systems along arcs that go from here down there contain a white dwarf and an M dwarf or K dwarf. And so it's trivial to find them, and there are more than 2,000 or so now. And the mass distributions that I showed you before come from this sample. So we want to look for systems that are more massive, both in terms of the companion and the progenitor. And so the next step is that you say, well, we need to move from an optical U minus G color into the ultraviolet, and we selected a sample of about 7,000 F, G, and K stars that were identified with the RAVE survey. That's a spectroscopic survey carried out in Australia, for which there are stellar parameters, surface gravities, temperatures. And these are shown here as a grayscale. So these are all main sequence stars with RAVE spectra. We cross-match that with the GALEX survey and show here the far ultraviolet minus near ultraviolet color, and find then a few hundred stars that are FGK stars in the optical, but they have a far ultraviolet excess. And so the next thing you then do is, again, you use HST, and it turns out we did that for 10 stars so far. So we had, in cycle 21, 10 orbits to observe 10 candidates, and turns out 9 of these have a white dwarf companion, 1 has a subdwarf, so that's 100% efficiency. So that means that, so these were 10 stars out of this sample, so it means that these are probably all white dwarf companions to FG or K stars, and there are very, very, very few known before this work. So what we got is then, in terms of observations shown here, that's the spectral energy distribution in microns and log f lambda, and it just illustrates why, if you do that only at optical wavelength, you have no hope, because these are the optical magnitudes. This thing just gave up. These are the optical magnitudes. So if you, this is the U band. If you look in the optical, this is the U band. Your white dwarf is 3-4 orders of magnitudes fainter than your F star in this case. However, if you move into the ultraviolet, the F star dies and your white dwarf shows up. Okay, and so we can fit the white dwarf Lyman alpha profile. We have radial velocities for that star, and we can disentangle all the parameters, and the important things are highlighted here. We have a white dwarf with a mass of 0.5 to 0.7, so not great constraints. That will again become better if we have a Gaia parallax for that star, because then we can use a mass radius relation and kind of a flux scaling factor. We can get that down to a few percent. And we have a companion star of about 1.2. Now what does that mean? That means when this system evolves into a semi-detached state and starts mass transfer from this star to that star, we will go through thermally unstable mass transfer, because you move mass from the more massive to the less massive star. That shrinks the orbital period to conserve angular momentum, and it may either lead to a merger or it will lead to a phase of very high mass transfer, and this very high mass transfer leads to stable shell burning on a white dwarf. And so we call that thing the first pre-super soft X-ray binary. But it doesn't have a large mass. It will grow if it goes through a thermal timescale mass transfer. It will grow, and it may end up one day as one of those cataclysmic variables with enhanced nitrogen depleted carbon. That brings me to my conclusions. One of the few facts that I've shown you is that the white dwarfs in cataclysmic variables are massive, and massive really kind of by a lot compared to single star evolution, and even more so compared to most common envelope evolutions where you truncate the mass growth of the core so that can't reach the full mass. Some of them can grow, could grow, probably have grown in mass during a super soft X-ray binary phase. So they were a steady shell burning source at some point in their past. And 15% of systems that cataclysmic variables that we see today have this enhanced nitrogen to carbon ratio, and so went through this route and could have grown their white dwarf mass. That leaves the whole rest, that leaves kind of 85% with a mass that is actually too high. They could have been born with a massive white dwarf. We haven't found any so far. We would need massive early B-type for most of them, and that kind of runs into a bit of problems with population models. And the other thing is, we know thousands of low mass white dwarfs, 0.5 solar masses plus K and M dwarfs, that would become cataclysmic variables that should be representative of what we see today, but we just don't find any system in the state of being a cataclysmic variable with a half solar mass white dwarf. So you need to get rid of these. And Matthias Schreiber just published a paper where he comes up with some speculative way of doing exactly this, of basically terminating these systems before they turn into cataclysmic variables. So calling them pre-CVs would then be a complete misnomer, because they die before they ever become cataclysmic variables. And then the third thing is kind of to challenge the theorists and say, like, are you really so sure that you can't retain some amount of mass during a classical nova eruption? And so that is kind of going against 40 years of work. But some people, like Sumner Starfield, dare to do so and think, well, maybe classical nova theory has enough uncertainties that it's worth to revisit that, and maybe you can grow to some extent in classical nova. Through classical nova, you can still grow the white dwarf to some extent. And it doesn't really matter how we will solve this in the end. The bottom line is that our understanding of compact binary evolution and binary population models is broken, because we can't explain this fact up here. So we need to change something, maybe several things, to explain these high masses. Now, the physics that underlies all these models is the same for double degenerates, for low mass X-ray binaries, black hole binaries, cataclysmic variables, and so on. So if something is broken and we can't explain that fact up here, then it means that whatever you do with binary population models will have some impact on type 1a rates from whatever model you think about. Thank you.
Any questions for us?
How does it apply to magnetic CVs? Is there any parallel or?
We have very, very few reliable masses because the methods that I showed you so far can't be applied to magnetic systems. They need to have a disk to be able to measure the mass. That goes back to the light curve modeling. My hope is that with this HST project that we are doing, we will measure some masses of magnetic stars. The one system that I'm aware of has a relatively low mass, 0.6, but that's statistics of 1.
But in terms of theory-wise, or black hole theory-wise,
Yeah.
how do you see much difference?
People ignore magnetic systems. So most binary population models ignore magnetic systems because they say that's a 20% effect and therefore we just ignore. Because we don't know how angular momentum loss in a binary works if you have a strongly magnetic primary star.
Since we're talking about single-degenerate progenitors, have you looked at other interacting binaries as potential progenitors? An example is the symbiotics, which also contain a white dwarf, and wind-accreting systems. Now, if you go with a slow dumping of material on the white dwarf, and you have a relatively high mass one dwarf, and some of them we are talking about one solar masses, can you dump enough to detonate in a supernova without this nova type?
I personally haven't looked at them, but there are many people who have. They're quite rare. So yes, could work, but there are not that many of them. There are some arguments that people say that you don't find giant companions in supernova remnants, and they argue that that's an argument against symbiotics. I don't know if that's really strong, but that's one of the arguments out there. But
there are two camps on that.
yeah, I know. That's why I did the poll at the beginning.
You would expect nova outbursts in that pathway as well. So.
Yeah. No, the symbiotic.
You feed them slow.
Well, no, I don't think. It doesn't really matter. I don't think how much.
Well, Sumner is working on the slow feeding.
Yeah.
Right?
Like slow feeding in general is bad because slow feeding means that you get in that you ignite under very degenerate conditions and you get a very violent nova eruption. So you want actually to feed very fast, and a lot of the recurrent novae are in symbiotics with a giant donor because a giant can drive a very large mass transfer.
About the ones that grow in mass during the supersoft phase, what can you say about the orbital period distribution of those systems?
That is within the small numbers that we have, it's fairly flat. So these are these red systems down here. So they can evolve below the canonical minimum of normal cataclysmic variables because you end up with a relatively dense core of a previously more massive star. So you can be Rush-Lobe filling at much shorter orbital periods. And they don't seem to care, but that's kind of, well, again, number statistics of 2 or 3. They don't seem to care about the period gap because they are not driven by magnetic braking, but by dynamical.
And the green thing is the normal CVs?
The green thing is normal CVs with UV spectra. And the white thing is all normal CVs.
If there's no other questions, let's take